Simple harmonic motion and circular motion. At first sight it may seem as though simple harmonic motion and circular motion have nothing in common. However, they're both repetitive cycles, and if we observe circular motion from the side, as we're going to do here, this is looking at an object from above, clearly exhibiting circular motion. Here we're looking at the same object but from the side, and this appears to be exhibiting simple harmonic motion. We can take the maths of both motions and combine them for circular motion and simple harmonic motion. I'm going to start with frequency, the number of complete cycles per second measured in hertz. This is the same for both motions and is given the symbol lowercase f. Next, the time period, which is the time for one complete cycle measured in seconds. This is given the symbol capital T and is found from 1 over the frequency. Alternatively, we can say the frequency is 1 over the time period. Next, the property angular velocity, which really relates to circular motion. This is given the symbol omega and is measured in radians per second. There are 2 pi radians in one complete circle, and this is in the time period t. So we can say the angular velocity omega in radians per second is given by 2 pi over t. But t is 1 over frequency, so we can also say that omega equals 2 pi f. We can use the same property for simple harmonic motion. Then we can substitute from these formulae into these to give time period is equal to 2 pi over omega, or frequency is equal to omega over 2 pi. So we have the same sets of equations for circular motion and simple harmonic motion. From simple harmonic motion we've seen that the acceleration a is given by minus 2 pi f squared x, where x is the displacement. But as omega is equal to 2 pi f, we can write the acceleration a being equal to minus omega squared x. Also, when we have maximum displacement at the start at t equals 0, we have the formula x is equal to a cos 2 pi ft, and so we can write that x is equal to a cos omega t. Combining these equations gives the acceleration a being equal to minus omega squared amplitude a cos omega t. It can also be shown that the speed v is equal to amplitude a times angular velocity omega sine omega t. For all these equations you must remember to have your calculator set in the radians mode. In any calculations you'll be provided with the formula you need, although you may need to combine some formulae or substitute here and there to get the suitable equation. Just summarizing the different terms, f was the frequency in hertz, t the time period in seconds, omega the angular velocity in radians per second, x the displacement at time t in meters, t the time in seconds, capital A the amplitude in meters, v the speed in meters per second, and a the acceleration in meters per second squared.